Hi, welcome to my video on object detection and localization. Here, I will firstly talk about the theory behind the object detection and region-based approaches, and then in the second part of the video, I will give you a tutorial on AWS on how to run your models and train them and effectively test them. So let's begin. Firstly, I would like to talk about the different tasks that are there in computer vision. So first is the task of classification, where we take an image and try to find out if a particular object of a particular class is contained in that image. What I mean by that is that if in the given example the image contains cat, our model will try to predict whether this entire image contains a cat or not. The cat can be located anywhere in the entire image. Then we have the task of localization. This is a task where we want to find out where exactly is the particular object located in the image. But in localization, we can only find one particular object for a particular image. In object detection, we further extend the task of localization. Here, we are trying to figure out whether there are multiple objects in the particular image. The example shown here shows a dog, a cat, and a duck in the image that has been bounded by the boxes. The final task is the task of segmentation, where we try to find out what probability of each pixel belonging to a particular class is. So here we can see the three animals have been distinguished from their background, where a cat, a duck, and a dog are clearly marked with particular boundary that represents the object in particular rather than a bounding box around it. So moving on, I would like to first explain to you what neural networks are. Neural networks are a family of functions which take a very loose inspiration from the brain that are used to approximate functions that have a large number of inputs. They are an example of nonlinear hypothesis where the model can learn to classify much more complex relations. It also scales better with logistic regression that did not have a large number of features. So we see from this diagram that the input layer and hidden layer and output layer are written on the image. So these are the three layers that basically define any neural network. So the input layer will have the input that has been given to the model. The hidden layers are the particular layers that try to learn a representation from the data, and the output layer will give the output of the particular solution that our neural network is designed to give. This diagram represents an artificial neuron. The artificial neuron has weights and biases which are multiplied with a dot product and are passed through some kind of a nonlinear activation function. What a nonlinear activation function will do is help us learn the different variations of a same class object. These variations can be learned better as we use the output from the previous layers rather than a linear classifier where we use same set of weights and try to train it on a particular set of data points. This shows the various activations functions that can be used. The first is a sigmoid function, the second is a tanh, and the third is a relu function. Sigmoid is not used anymore, but tanh is used in certain cases, and relu is a very good nonlinearity function. This is the one that is recently introduced and the one that is highly used now. The relu function is very good because when doing backpropagation, the gradient doesn't die but it becomes constant, so it is easier to handle. Next, I will talk to you about the various steps that are there in neural network training. First, we initialize the weights randomly after the architecture is designed. We then do a forward pass, get the results, calculate the loss on those results. The loss here is the difference between what the actual output should have been and what the output our model has given. So that particular loss or the difference is calculated and that is backpropagated to the network. What we mean by backpropagation is that we'll send that loss through the entire network and try to find out what a particular neuron would have the effect on the particular loss in the final output. So we change that particular neuron in accordance to the loss that it has caused to the final output. This loss is then used to again and again calculate over the set of data points that we have in our data set so that we get a closer representation of the learned space that our model has learned to the closer data distribution we can get. Now I'd like to talk to you about convolutional neural networks. Convolutional neural networks or CNNs are a class of neural networks that have been extensively used in visual recognition problems. These were introduced by Jan LeCun in 1998 when he used the image dataset to get some very good results. In 2012, AlexNet was the one that gave very good results for the ImageNet challenge, which beat the previous competitor by a large number of percentage points. So we see that convolutional neural networks have taken over the field of computer vision completely, as it can learn directly from the data itself and there is no need of hand engineered features. The same network can be used to learn a cow from a dog, can be used to learn between two different set of plant diseases. So there is no new requirement of creating particular networks for particular problems. They are universal. This particular image shows the image of a typical convolutional neural network. So we have the input layer, the filter depth or different filters or different kernels that I will explain to you later that are there, from where we take the ReLU outputs, which is given to a fully connected layer, which will create a kind of a probability density about which class a particular image has an image which is belonging to. So now we will move on to the convolution operation. So what a convolution operation does is that it takes a filter or a sliding window that is run through the entire image. Here in this particular image you can see that a kernel or a particular filter that is applied through the entire output, and then for every position that our kernel is placed on the image, we take a certain kind of an output that is called a feature map. Now what a feature map does is that it takes the output of the entire convolution operation that has been performed over a particular image, and the, the feature map will have the outputs that have been passed through a nonlinear function or an activation function, which is usually a ReLU nonlinearity function that is used in the modern deep neural networks such as convolutional neural networks. So what these feature maps will do is that in the lower layers of the network or in the initial layers of the network, they will learn certain kind of representations from the data such as edges or small patterns. And as we get deeper and deeper into the network layers, we start seeing better and better representations of data being created. As here you can see that in the first few layers, the patterns detected are not that great, but in the subsequent layers we see the patterns getting clearer and clearer, which shows that deeper neural networks are easily able to learn the representations of data for multiple classes. In this diagram you can see different activation maps or the feature maps that have been created after a convolution operation. The feature maps are calculated so that they can be passed on to the further layers. We can imagine it as a set of images that have been generated by the model for the next layers itself. So particular convolution layer will create a set of activation maps. For example, if we have two kernels in this particular image, we will have 6 activation maps, and the activation maps will also be reduced in size unless and until we use the concept of padding. This particular shows that operation of convolution and the creation of a feature map. In the first image we see that the problem of the reduction in the size of the feature map. Here we see that a convolution operation is being done on the image and the feature map is being taken as an output. But in the second one, if we see that we can pad the input with zeros, or we call it a zero padding, this will help in retaining the same size of the input to the output. As you can see, in the first image we have a size reduction, but in the second image we don't have a size reduction. Next is the concept of pooling. Now this is a very good concept that uses the spatial size reduction and not the depth of the input tensors or the output tensors. This is very good as we sometimes need to reduce the spatial dimensions. By having less spatial information, we can gain computational power. By having less spatial information, also we have lesser number of parameters. So we won't have an overfitting problem. And also it gives some kind of a translational invariance in the image to our model. As pooling operation will reduce the spatial dimensions, we can do this in two ways. One is called a max pooling operation, another is called an average pooling operation. So what we do is that we slide a window over the input, take the maximum value in that window and put it in the output. So here we see that 6, 8, 3 and 4 come out of the red, green, yellow and blue blocks respectively. So these are the maximum values. In average pooling, we would just take the average of all these values and put them in the output. So in essentially we are reducing the size of the input so that in the output layers we can get better computational performances. The next images that I want to show is of a image that has been fed forward through a convolutional neural network. So we have the different filters learning some representations from the data, and then we have a pooling layer where we reduce the dimensions. Then again another convolutional which will learn the representations further, and then another pooling layer. And then we have the fully connected layers which try to produce outputs using a software activation where we get a probability distribution function. Now that I've talked about the basics of neural networks and the basics of convolutional neural networks, I would like to move on to region-based approaches. In these approaches, I would like to tell you about first the Rcnn, then I will talk about fast Rcnn, and then in the end we will talk about faster Rcnn. So what we have in Rcnn is that we try to form regions which we send to a convolutional neural network and then try to predict whether they belong to a particular class or not. So what we do is that in the input layer, we do is that we take a method such as selective search to propose regions. What we are doing here is that we are taking selective search to create boxes on the input image which will be further sent to the convolutional neural network. Here we can see that we are warping the image regions, or we are resizing them to a particular size so that the fully connected layer can take in the input. Once we send the input through the convolutional neural network, a forward propagation is done. Then the features are saved onto the disk. Then we perform SVM on top of the input that has been given. We have one SVM per class. That is, if there are say supposedly 20 classes in our dataset, we'll have 20 different SVMs and plus one more SVM for the background class. We also have some kind of a regression so that we add a corrective feature to our bounding box regressions. Here this slide shows the selective search method. In the selective search, what we are trying to do is that we are trying to merge different pixels with the neighboring pixels. And as we merge more and more pixels, we get blob or blobby regions, as you can see in this image. As we merge more and more, we get lesser and lesser blobs. That means we get well-defined regions. Essentially, this is what we are trying to do in selective search. So the middle example shows a very good selective search method which could be proposed for a particular input image. So what we do is that while training, we remove the last layers of a fully trained network such as an LXN, which is used in this particular Rcnn. We take the input output layers which were there for 1000 classes and replace it with 21 classes, where 20 would represent the classes in the Pascal VOC dataset and the one class would be the background class. Then what we do is that we take the warped images or the proposed regions in the image, send them through a convolution layer and extract the features for that particular image. Once we have those features, we do a SVM classification on top of it, and also we add some kind of a corrective measure to the bounding box coordinate. In the image below, you can see that first is a good proposal. The second and the third proposals are not that good. So a bounding box regression will try to correct these and try to learn a better bounding box creation for the final image. Next, I want to move on to is fast Rcnn. So the problem with Rcnn was that it took a lot of time at testing. What I mean by that is that in this particular image example, you can see that we will send all the 2000 selected proportions of the image to the neural network. So this is a very computationally expensive task, as sending 2000 image proposal through the network is a very bad wastage of computational power. To mitigate this thing, we have fast Rcnn, which was introduced by Ross Gersich and his team again. In fast Rcnn, what we have to do is that instead of running all the proposed image regions through the network independently, we run the entire image at one go. So what we are doing in this images that we are taking the entire input image, sending it through the network and getting a convolutional feature map from a convolutional fifth layer. These feature maps will be used to generate the regions of interest. So in regions of interest, what we'll do is that we'll calculate the size of the bounding box to the scale of the size of the feature map. So if a bounding box is bigger in the input image, it will be reduced to that particular scale in the feature map. After that, what we do is that we try to warp or create a smaller region or a particular fixed size input for the further layers that are fully connected, as they will only accept fixed size inputs. So in the proposed regions that have been given from the selective search method, now what we do is that we create smaller regions that will be fed into the fully connected layers. Once it is fed to the fully connected layers, we calculate a softmax activation where we try to find out the classes that it will be belonging to for the particular object detected. We also have a linear loss for the bounding box regressions, which will try to act a corrective feature again. This will be a combined loss, which is during the training time, that is calculated a multitask loss, which is again the summation of linear softmax and the linear bounding box regression loss. In the ROI pooling layer, as from this diagram you can see, is that we calculate the corresponding bounding box for the smaller feature map, and from that particular bounding box of the feature map we transfer it to a max pool within each grid cell. So what we are essentially doing is that we are trying to reduce the size of the different sizes in the feature map region proposed to a fixed size vector where we are having the different activations which will be sent to the network further to be classified as particular objects. I want to show you an example of how the ROI pooling layer really works. We have an image and the corresponding bounding boxes for the faces in that image. We now take the feature map outputs from the convolutional neural network. Here on the left, we have the feature map activations of these images. The image on the green box has been highlighted. The image on the right shows the bounding boxes around two images that have been marked in the original image. In the image that have been bounded in the red color are of the same aspect ratio as that in the previous image. Here we can see that. Now what we do in ROI pooling layer is that we do a max pool within each grid cell so that we have a particular size that can be passed on to the fully connected layers. So these two red bounding boxes will further be resized to the outputs as these two images. So these two images will be sent to the fully connected layers for further classification. Now I want to come to the concept of faster Rcnn. Faster Rcnn is an even better architecture. So the problem with the previous approach was that even the selective search was a slower process. To even speed up more, we have the process of faster Rcnn. In faster Rcnn, we have something called a region proposal network. Instead of using a selective search method, we have a neural network that learns to propose regions. For this, we use the concept of Rcnn network. So what we do is that on the feature map that have been generated after the convolution layers, we slide a window upon it. Then we create cake anchor boxes. Now anchor boxes are the proposed boxes that are generated by the Rcnn or the region proposal network. For this particular paper, they used the anchor boxes of three different scales, that is, three different sizes and three different aspect ratios. So in total, they had 4x9 anchor boxes for a particular sliding window and 2k scores as an object or not an object in that particular anchor box. To get a clearer picture of what I just said, in this image we see the two boxes that have been generated from the previous example that we showed. In this, the Rcnn will run a sliding window of 3x3. This 3x3 window will generate anchor boxes or which can have an object or not. So we first want to check in those particular boxes whether they contain an object or not. Here, at this particular point of time, we are not trying to calculate whether they have a class of an object which we are trying to find, but we are just trying to classify a box whether it has an object or not. Basically, what the region proposals do is that they run a 3x3 window on top of the feature map and generate key anchor boxes. And those key anchor boxes have to be classified whether they can create object or not. And also, we try to improve the bounding box coordinates for them. So now we have a fourfold loss for our faster Rcnn. There's a classification loss from the region proposal network which tells there is an object or not. There's a bounding box proposal loss, and then there's an object loss from the classification itself where we try to determine whether which class this object belongs to, and then there is another bounding box loss on top where we try to refine the bounding boxes that have been created by the RPN. A comparison shows that faster Rcnn is the fastest among the three. This is because it uses RPN and selective search. In fast Rcnn, we don't use RPN. That is why it is a bit slower because selective search takes approximately 2 seconds. And Rcnn is the slowest because independently all the proposed regions are sent to the convolutional neural network and the advantage of ROI pooling layer is not taken. So we see that faster Rcnn gives a lot of speed up and is applicable to real life applications where it is needed on the edge. Hi, welcome to the second part of my video. Here I will show you the demonstration and implementation of a Git repository for object detection. So the steps to implementation are: first, to find a dataset to use. A very good dataset to use would be a dataset that is widely used in academics and has been well researched upon. So for this, I will use the MS COCO dataset, which stands for Microsoft Common Objects in Context dataset. From there, I will use the 2017 version of it. So, for an object detection task, these datasets come already labeled. But what if you want to use your own dataset and label it yourself? So for that, first I'll demonstrate a tool called labelimg, which can be found on Git repository of this person, which he released. So this is the repository for labelimg. So this is a tool which can be used for annotating your dataset, which is used for further training it on models where we can detect objects and various classes that we want to detect for a custom dataset. So for this, I'll show you the first installation process. So let's go to terminal now. The terminal is already open. So now the first step is that we need to download the repository. The repository can be cloned onto your desktop or whichever folder you want it to be in. So I'll do a git clone of this repository. As it will take some time, I already have a downloaded version of this repository and I will go to that. So I will go to desktop and labelimg folder. Now there are some dependencies that need to be installed. So we'll first install Qt. Qt is the framework that this labelimg works on. Qt is like tkinter, it's a GUI library for Python. But this was already installed as I had used this before. So I'll also do the other one, that is the libxml. But libxml, as you can see, is already installed. And this step is not required for this particular instance as I've already installed this. So now I'll go to the labelimg folder and from there I'll open the labelimg file. Well, now labelimg is open. So we'll first go to the folder from where we want to select the images, and then we'll go to the folder where we want to save our annotated images. And now we can start labeling. So for example, in this image we have a woman who is standing at the window. So if we want to mark it, we'll press W and draw a bounding box around it. Okay. So now that we see that we haven't assigned a label to it, so we'll say person. We can also move around the bounding box if it has been incorrectly placed, or in case if we have a lot of persons or people or things of same class, we can use the default label over here, and every time we draw it, it will show up. as a person. We can move on and keep labeling. So for example, if you want to label this stop sign, we can draw a bounding box around it and say that it is a stop sign. It is labeled as a stop sign. Like this, we can label an entire dataset of as many images as we want. Moving on, after labelimg, we can go to our dataset. The dataset I will use is called Microsoft Common Objects dataset, which I already told you. This dataset has been annotated already, so we'll download this. Instead of downloading it on my local system, I would now like to first tell you how to set up your AWS instance for deep learning. Now, AWS provides very good elasticity, that is, we can scale up our deep learning training as we want to on the cloud and on the go. We don't need to buy the expensive hardware, but we can use the cloud services to quickly train our models without the hassle of setting up the entire system. So for this, Amazon provides Amazon Machine Images or AMIs, which are suited to particular needs. So for this, I'll use a deep learning AMI that Amazon already provides. This saves me a lot of time for installing all the dependencies, like say if we're using TensorFlow or PyTorch or everything that can be used for deep learning, it comes already installed. So now I'll show you the demo of it. I'll first go to my AWS account. I'll go to EC2. I have chosen Ohio region as it has the latest P3 instances. Now P3 instances have the V100 server GPU that is having more than 5000 CUDA cores and can train very fast. So we'll first go to instances, and as you can see that don't have an instance right now, we'll do a launch instance. So we start creating an instance. So we first use the operating system we want to use on it. As I told you, I will be using a deep learning AMI, so I'll select that. Now I need to select the type of system that I want to use. Is a wide variety of systems that AWS can provide us to use, but for the processing of images and large data sets, we would like to use the latest hardware that is there. P3 compute provides the latest hardware, so you'll use P3 2x large. Now this step can be skipped, and now we'll add storage. So 75 gigs will be an enough storage capacity as our dataset is of 18 GB, so it will be sufficient for us. And now we'll review it and launch, and I'll choose one key pair through which I will log in to my AWS instance. As you can see, this instance is being launched right now. We have to wait for some time for it to get launched. Now our instance is running, so we can connect to it, but for that you have to first change the permissions for your PEM file, otherwise we cannot connect to it. Now on my terminal, I'll first quit the labelimg, and as you can see, I previously didn't mention before, but you can see a few images have been labeled here with the particular bounding boxes. So I'll first launch into my EC2. But permission has been denied here. So I'll first do a ch. Oh, this file wasn't there. So I'll go to desktop first. Yes. So now we can see that we have been connected to EC2 instance. Here we can see a lot of different network environments have been set up already. So these all are the various frameworks that we can use for deep learning, and they come already installed with CUDA 9, and it is very fast, as we just used like around 1 or 2 minutes for setting it up. Usually it can take up to hours to set such a system up. So firstly, I'll make a few folders in it so that we can organize our data. I'll do an mkdir data. I'll cd into that. Over here, we would like to first download the dataset. Dataset can be downloaded from the official website of MS Coco. Here you can see I'm downloading the training dataset. And one more advantage of using AWS is that it provides us very fast network speed. So here you can see approximately 1 gig of bandwidth is being used. That is very expensive for systems that we have outside of the cloud, but in cloud we get the benefit of very fast speeds. So it will be downloading. Now we can see that our dataset is downloaded. We also need to download the corresponding annotation files for it, the bounding boxes that have been marked for it. Now we have also downloaded that. So we'll first unzip the training folder. This will get unzip. It will take some time because there are a lot of images in this folder. All the files have been extracted now. So now we'll also unzip the annotations folder, but first we'll move it into the training folder. And now we'll unzip the annotations folder here. Now our annotations have also been unzipped. Now we can remove the training.zip file. Now we will have to install the repository for Rcnn, but before that we'll have to activate the TensorFlow on the deep learning AMI. So a simple command for source activate TensorFlow underscore p36 will activate that. But the first time, as we are using this repository, it will have to first set it up, so it will take some time here. Now we see that the TensorFlow has been activated. Now we can run a repository on it. So first of all, we'll have to go to the GitHub repository link. From here, we'll download it using a git clone command. We'll go to git repos folder. Here we'll see, okay, so there is an already a KRS Rcnn that has been downloaded. Now we'll do an install of this repository. Well, this is also complete. Now there are a few dependencies that need to be installed for this. First is the Python image library below, which has been installed, and the Python library, and Python also has been installed. So now we'll also have to install PyCoco tools, which is a set of tools that are required for using Coco dataset by this particular repository. This has also been installed. Now we'll have to train our network. So we'll go to the training file. In this, we'll go to the bin folder. Here we can see the train.py file. To train it, we have to do Python, the name of the file, the name of the dataset, and the path to dataset. home/ubuntu/data where our dataset is located. And now we'll have to wait for the model to execute. The model will load now. Now we'll begin the training process. First of the 50th epoch will begin now. It will take some time for the first epoch to run as it is loading all the data. Now we can see that the training process has begun, but as this is running on the cloud with the fastest GPU, we can see that still it might take up to 2 hours for one epoch to get completed. And this time is reducing, but on an average it will take a lot of time. So to prevent the cloud costs to accumulate too much, I'll use a pre-trained model that the repository people have released, and I'll use that to test some images. Once we train our model, we would like to test whether our model is working accurately or not. We would like to perform some tests on the test dataset which our model will not see during the training phase. As it will not see the particular images during the training phase, we can check how well our model is generalizing on the general data that could be thrown at it in the real world environments. So for this, I have written a test script. This is a similar script that was found on the repository itself, but I've modified it to my needs for this particular example. So now, as you can see, this has a file name retinatest.py. So we simply have to run this file, Python retinatest.py. Now you can see that all the images that were there in the test set are being processed, and it is a GPU, so it processes it very fast. The testing process is complete. Now we'll go to the output folder, but we can't see the output from the cloud itself, so we'll have to first download the output folder. For this, I'll zip it. The files have been zipped now, so now I'll have to download them. To download from AWS, we'll have to use SCP. So we'll do that on the desktop itself. So this will not be from the terminal of the console from AWS, but from our local system. So we'll go to desktop where our PEM file is. We'll do an SCP. So here we have to copy from AWS to our local system. So we'll select path to file of the PM file, object detection. Then we'll have to give our IP that has been assigned to us, the DNS that has been assigned to us. Now the file is being downloaded. Okay, I think I made some mistake in the naming. Oh, I think I forgot to add O at the end. The files are being downloaded to the desktop. We'll now open this folder and check out the output. Here we can see that different objects have been identified. As you can see, various images with people in it and various other classes, and these images have been found, have been detected very well. So this was a tutorial on object detection. Here I first explained the concepts of neural networks, then I explained the concepts of convolutional neural networks, then I explained the concepts of Rcnn, then went to fast Rcnn and then to faster Rcnn, and then I gave you a demonstration of the entire process of how to start labeling your dataset, how to set up the AMI on Amazon, and then how to run a repository. For this particular video, I used Rcnn repository, which is a very good and very well performing repository. And from the results also we can see that this repository is very good with the scale and with different objects being recognized very well. So this was my video seminar on the object detection. Thank you for watching and have a great day.